Have you ever wondered if there are truly universal rules, laws of nature that apply to everything, no matter how small or how big? A concept that sets a fundamental limit on what we can possibly know about the very building blocks of our reality. When we talk about Heisenberg's uncertainty principle, the direct answer is absolutely yes. This profound principle truly applies to all particles throughout the universe, from the most elusive subatomic particles to composite ones like atoms and even molecules. Now, let us dive into the fundamental reason why this is the case. Heisenberg's uncertainty principle is not a statement about the limitations of our measuring instruments or our ability to observe things. Instead, it is a deep, intrinsic property of nature itself, rooted in the wave-particle duality that all quantum objects exhibit. Every particle, whether it is an electron, a photon, a proton, or even a tiny dust particle, possesses both particle-like and wave-like characteristics. The principle states that certain pairs of physical properties, such as a particle's position and its momentum, or its energy and the time over which it is measured, cannot both be known with perfect precision at the same time. The more accurately you try to determine one property, the less precisely you can know the other. This inherent fuzziness is a cornerstone of quantum mechanics, describing the very fabric of reality at the smallest scales. So, how does this manifest in the real world for all particles? While the principle applies universally, its effects are only significantly observable at the microscopic quantum scale. For everyday objects, the amount of uncertainty predicted by Heisenberg's principle is astronomically small, making it practically negligible. However, for tiny particles like electrons orbiting an atomic nucleus, this principle is vital. It fundamentally prevents electrons from simply collapsing into the nucleus, as a perfectly defined position would imply an infinitely uncertain momentum, leading to a minimum kinetic energy that stabilizes the atom. This is a critical aspect of why matter itself is stable. This universality extends beyond the well-known electrons and photons. Even larger, more complex quantum entities, such as full atoms or even small molecules, are subject to this same inherent uncertainty. The degree of this fundamental uncertainty is scaled by a tiny but ever-present value called Planck's constant, which is approximately 6.626 times 10 to the power of minus 30 for joule seconds. This minuscule value is precisely why we do not notice the principle at our everyday macroscopic scale, but it reigns supreme in the quantum realm. It is a powerful conceptual tool that differentiates quantum mechanics from the classical physics we experience daily. Understanding that Heisenberg's uncertainty principle applies to every single particle, without exception, offers us a profound insight into the intrinsic nature of our universe. It highlights that there are fundamental, unavoidable limits to our knowledge of complementary properties, guiding our comprehension of atomic stability, quantum phenomena, and the very structure of matter itself. This principle is not a barrier, but rather a window into the truly unique and often counterintuitive behavior of the quantum world.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.